In this video we are going to look at how we can use significance tests on values of the correlation coefficient. So the data here refers to the time taken by a group of 20 pupils to complete a history assignment and the mark obtained by the students for this work when it was assessed by their teacher. Looking at the scatter diagram to begin with, we can see that there is weak positive correlation amongst the data points. That is verified if we look at the correlation coefficient for the data points, which is 0.3605. What we would really like to determine is whether the sample provides evidence that there is a positive correlation between the time spent by all pupils on this assignment and the marks given by the teacher for their results on this assignment. In other words, does the result obtained from this sample provide evidence that in general, the longer a pupil spends on the assignment for the teacher, the better the mark obtained? So we're going to set up a significance test on the population correlation coefficient. And in the example that we're considering, we're asking whether the result obtained provides evidence that there is a positive correlation between the population of all time spent on the task mark obtained by the task points by all pupils doing the assignment set by the teacher. So let rho be the correlation coefficient of the data points t, m, where m is the mark gained by a pupil who spent t minutes on the assignment, for the population of all pupils who have been set this assignment by the teacher. Then we want to determine whether or not the sample that we considered on the previous page provides significant evidence that the population correlation coefficient, that is rho, for these data points is positive. We're going to set up a significance test using a critical region to make this decision. Our key steps, first of all, we've got to define the variables. So rho is the correlation coefficient consisting of the population of all Tm values for this assignment set by the teacher concerned. Our null hypothesis is going to be that rho is 0, that there is no correlation. Our alternative hypothesis is going to be that rho is bigger than 0 because we were being asked to find whether there was evidence that there is positive correlation. The test statistic is going to be the information that we've got from the sample. So that is R, which is the correlation coefficient for a random sample of 20 pupils doing this assignment for the teacher. Now, unfortunately, we can't state what the distribution of R is. It's beyond the level of this particular unit. However, we have got a set of tables which we will use to find the critical region in step 4. We need to state the significance level. Well, since we're simply being asked for evidence in this case, we'll use a 5% significance test. We only want to accept the alternative hypothesis if the value of R is significantly bigger than 0, so it's going to be a one-tailed test. To find the critical region, then, we're going to have to use some tables. Now, the tables that are provided, and you'll be given a full copy of these tables by your teacher, give us the critical values of the product moment correlation coefficient under certain assumptions. The assumptions that are made here are actually usually rather glossed over, so you don't really need to worry about those too much at this stage. How do we use these tables? Well, the first thing we must do is find out the size of the sample, which in this case was 20. So we find the rho corresponding to 20. We must then recall whether we are using a one-tailed test or a two-tailed test. We're doing a one-tailed test in this case, so we go for the top row at the top of the table, find the significance level, which is 5%, and then we go down that column until we hit the row for n that we've got. So the critical value for our significance test is 0.3783, which tells us that obtaining a value of r which is bigger than 0.3783 would be very unlikely under the assumption that the null hypothesis, that the population correlation coefficient is 0. So if r is greater than 0.3783, we're going to accept the alternative hypothesis, and if r is less than 0.3783, we're going to say there is not any reason to reject the null hypothesis. So the critical region then is r is greater than 0.3783. We should just at this stage comment, though, that if our alternative hypothesis had been that rho was less than 0, then the critical region for the test would have been r is less than minus 0.3783. So carrying on with the significance test, though, that we've got in this case, then we've obtained our critical region for the test, and having obtained the critical region for the test, we can now apply it, giving the conclusion in context. So our decision rule then is if r is greater than 0.3783, then there is evidence at the 5% level to reject the null hypothesis in favour of the alternative hypothesis. Otherwise, we should conclude there is not enough evidence to reject the null hypothesis. So in this case, we had the sample gave us r equals 0.3605, which is not in the critical region. Our conclusion, it should be that there is not evidence to reject the hypothesis that rho equals 0 in favour of the hypothesis that rho is bigger than 0. So the sample does not provide evidence that the longer a pupil works on the assignment, the better the mark achieved. Or equivalently, we can say that the sample does not provide evidence of a positive correlation between the time spent and the mark achieved on this task. For our second example, we consider a physics teacher and an art teacher in a school who wonder whether there is very strong evidence for correlation between the individual performances of pupils in Year 9 in their two subjects. Separately, they decide to calculate the correlation coefficient r of the exam results of a random sample of 10 Year 9 pupils in the two subjects. So we've got to set up a significance test and determine the critical region for the test. And then we've got to describe carefully the conclusion each of the teachers would make if the art teacher obtained a value of r equals 0.347 from her sample, and the conclusion the physics teacher would take if she achieved a correlation coefficient of minus 0.814 from the sample that she took. So let's start by setting up the significance test. Let rho be the correlation coefficient of the marks in art and physics for all the pupils under consideration. The null hypothesis then is that rho is 0, because we're looking to see whether there is any correlation or not. So the null hypothesis is going to be there is no correlation. The alternative hypothesis in this case, because we are looking to see whether there is any correlation at all, then we're going to have for the alternative hypothesis rho is not equal to 0. We're looking to see whether there's positive evidence for positive correlation or negative correlation. The test statistic is going to be the correlation coefficient between the exam results in physics and art for a random sample of 10 pupils. We're looking for very strong evidence, which means that we need to be using a 1% significance test. And it's definitely going to be a two-tailed test because we're going to want to accept the alternative hypothesis if the value of R is surprisingly large or surprisingly small under the assumption that the value of rho is actually equal to 0. So it's a two-tailed test. We will again need to use the tables to find the critical region for the test. We're dealing with a sample of size 10. This time we are dealing with a two-tailed test, so we need to use the second row up at the header of the table. And we want a two-tail 1% test, which is right over in the right-hand column. So the critical value that we have got is 0.7646 for a two-tailed test with n equals 10 and a significance level of 1%, which means that values bigger than 0.7646 or smaller than minus 0.7646 will be values in the critical region. So the critical region is R is less than minus 0.7646 or bigger than 0.7646. So we can now move on and add now that we know the critical region, we can state the decision rule. If the value of R is smaller than minus 0.7646 or bigger than plus 0.7646, then there is very strong evidence to reject the null hypothesis in favour of accepting the alternative hypothesis. Otherwise, there is not sufficient evidence to reject the null hypothesis. So the art teacher had a correlation coefficient of 0.347 for her 10 students. This is not in the critical region, so the art teacher should conclude there is not very strong evidence to suggest correlation between the physics and the art results. The art teacher has decided to accept the null hypothesis. Now it's possible that the alternative hypothesis may be in fact true. So she may have made the mistake of accepting the null hypothesis when the alternative hypothesis is in fact true. So it's possible that the art teacher has made a type 2 error. The physics teacher obtained a value of R of minus 0.814, and her value is in the critical region, so the physics teacher should conclude that there is very strong evidence of correlation between the physics and the art results. So the physics teacher has accepted the alternative hypothesis. It's possible, though, that she made the mistake of accepting the alternative hypothesis when the null hypothesis is in fact true. This is a type 1 error, and the probability of this happening is the significance level of the test, which in this case was 1%. Finally, here's a question for you to have a go at before you go back to your next lesson. And in the next video, we'll be having a look at how we can use p-values to conduct significance tests on correlation coefficients. But for the moment, that's the end of this video.